and what are the problems of redundancy, and how to decompose. After decomposition means at the time of decomposition, we need to ask two questions yourself. All these things we discussed in the last two classes. I think everyone is understood, right? Hello? All of you understood? Second time I explained in the last class. Hello?
Yes, sir.
Yeah. So today we are going to learn functional dependency. Here, if we know already what is the use of functional dependency. Here, when we want to decompose a relation because of the redundancy of the data in that relation, we have to decompose to avoid the redundancy problems. At the time of decomposition, we need to find the functional dependency. Now, in this class, we are going to learn what is the functional dependency, how to identify functional dependency. Is there any pre-defined formulas are there for the functional dependency? Mathematical formulas are there. We will discuss today. Here in the normal forms, in the next class onwards, we are going to discuss one by one normal form. Means every normal form is having its own functional dependency mechanism. So how to understand that functional dependency, how to identify the functional dependency, how to do that, we have to learn today. But in every normal form, we are having suitable functional dependency. Then how to apply, we can discuss. That's why today we are going to learn here what is the functional dependency and how to identify functional dependency. Is there any mathematical formulas out there? So that is what today's session we are going to understand. So that your normal forms are more easy if you understood this particular functional dependency. Are you clear? Are you clear about this? Hello? Are you clear about this? What today we are going to discuss? Yeah. Now, we are going to start with now we are going to understand functional dependency. Just I am sharing my screen. Is this visible? Is this my screen is visible? Hello?
Yes, sir.
Yeah, right. Now coming to the functional dependencies, as we discussed in the last previous classes. Here, a functional dependency, already I told you, in a relation or in a table, one attribute is depending on another attribute, or one attribute depending on more attributes, or more attributes are depending on single attribute. So that is called as functional dependency. Here, even I told you in a table, for example, relation R is there. Relation R contains X, Y, Z. These are the three attributes are there. Now if you take like this, now this Y and Z is depending on the X. Dependency means here if you know whatever the value is there X, based on that value Y, Z values are there. That is what in the last class we discussed. Yes or no? Yes or no? Yes or no?
Yes, sir.
Here in the same way, for example, X equal to 5, then compulsory Y is 10. X equal to 4, then compulsory Y equal to 8. Now again X equal to 5, then Y equal to 10. But here these values of Z values are not like that, different values. So that we can tell y is depending on x, so that we can write x determines to y. So this is the functional dependency in this particular table, because all y values are must be depending on x values in this relation R. So that here the functional dependency we are identified, the basic functional dependency we are identified, x determines to y. Understand? As per the last class, same thing I am discussed here. Clear?
Yes, sir.
Yeah. Now let R, just now I told you, just R be a relation schema and xy be a non-empty sets of attributes in R. Just now I told you just xy. Okay, non-empty means it contains some tuples. We say that an instance of R means instance, you know what is the meaning of R of R, satisfies the if the x determines to y. I mean, what is the meaning of y is depending on x. All y values are depending on x values. That is what function FD means, functional dependency. Remember, for shortcuts we have to use here. FD means functional dependency. FD is x determines to y if the following holds for every pair of tuple T1 and T2 in R. So what is the meaning? T1 of x equal to T2 of x. What is the meaning this? The T1 is tuple 1. This is the tuple 1. This is the tuple 2. The T1 of x means what is that? 5. T2 of x is what? 4. Then T1 of y equal to T2 of y. T1 of y is nothing but 10. T2 of y is nothing but 8. So that is T1 equal to T2. So when T1 x equal to T2x, T1 x equal to T2x, then T1 y equal to T2x. Means here 5 and 5 equal. Then this 10 are equal. So that is what exactly the meaning, what I just told you. So that is in functional, that is called functional dependency. That is x determines to y. Says that two tuple values in attribute x must be in association with two tuple values in attribute y. Yes, two tuple values, 5, 10, 5, 10. So these two are must be same. So that is a functional dependency. X determines to y. Clear? All of you clear this? All of you clear
Yes,
this?
sir.
Already, yeah, some examples earlier we discussed about that. Now, if you take one table, A, B, C, D, this is a relation. It contains 4 columns, A, B, C, D. Now, these are the tuples. Then when we are going to observe this relation, is there any functional dependency? Can you, any one of you identify any functional dependency here in this table? Please identify. Please check table only. Do you identify any functional dependency here?
Yes, sir.
Yeah, tell me, what is that? Hello? Is there any functional dependency you are identified in this relation? If the screen is visible, my screen is visible?
Yes, sir. It is.
Yeah. Can any one of you tell me what is the functional dependency here?
C is
Hello?
depending on both A and B.
Can you repeat again?
If, if A is A1 and B is B1, then C is automatically C.
Yeah, because here when you are observed, here A1, B1, C1, here A1 is there, B1, A1 is there, B1, A1 is there, B2. Then it is not possible. A, B is not depending on A, correct? First, you need to check these two columns. Yes or no? Because A1 is the B1, here A1 is the B2. So that it is not right, correct? Hello? Hello? Are you following? Hello?
It's the following.
Yeah. Now you take two attributes. There A1, B1. Wherever A1, B1 is there, C1 is there. Okay. A1, B1 is there, C1 is there, right? There A1, B2. Now it is changing. A1, B2. Then C2 is there. Then it is changing. A2 B1 is there. Again, it is changing B3. So that always C depending on AB. Always C depending on AB. So that we can write AB determines to the functional dependency of this table is AB determines to C. Are you clear? Are you clear?
Yes, sir.
Yeah, like that, we are going to identify the functional dependencies in a given relation. Because for that, generally, if you are identified a primary key constraint is a special case. So when your table is having a one column as a primary key, so you consider that is a special case. Because, for example, if you consider A is a primary key, the remaining all the attributes are depending on the primary. So that we can write primary key means A determines to B, A determines to C, A determines to D. Like that we can write it. It is possible. Because you know the primary key. You know, if I know the article number, then I can know your class. If I know the article number, I know your parent number also. If I know the article number, your pass percentage. If I know the article number, your subject failed, whatever subject you have failed. If I know the article number, sure, I can know everything related to your academics. Yes or no? Yes or no?
Yes, sir.
Because it is a primary key. That's why here remaining all the attributes in a relation must be depending on the primary key. That is why if a primary key constraint it is there in your table, it is a special case of a functional dependency. So that it is going to have all attributes in the relation placed with the role of I. Here all attributes are going to play with the particular primary key. So that here note it down. The definition of functional dependency does not require that the set X be minimal. The additional minimality condition must be met for X to be a key. Means if your relation contains a key attribute, primary key attribute, then here automatically remaining attributes are depending on primary key attribute. No need to verify. Directly you can write. So this is very important point. Please remember. Are you clear? Are you clear?
Yes, sir.
Now, one more important point also you remember here, this point. If X determines to whole, for example, in your relation, it contains so many attributes, okay, like that, your relation is there or X, Y, we are there. If in this relation, you are identify X determines to Y, means Y is depending on X, where Y is the set of all attributes. Means Y is nothing but it is a set of all attributes. Y is nothing but it is all the attributes. It is going to represent it to all the attributes. And there is some subset V of X. Here, V is a subset of X. If you write that V determines to Y, if the V determines to Y, means Y is depending on V, then X is a super. Simple, very simple. Here, very simple. Here we are telling all attributes with the help of Y, right? Here then this particular V determines to Y, then automatically here X is a super. Means X contains all the attributes. So this you can understand after understanding of so many examples this point, but you please note it down this point. Very important point it is. So many areas we can use this point. Okay? Is it clear? So practically, you can understand more clarity for this, how to define the super key easily. Hello? All of you clear?
Yes, sir.
Right. Now coming to the reasoning about FDs. FDs means functional dependencies. Here how we are going to define functional dependencies. Very simple. Here, for example, if you take one entity workers, here SSN is a primary key, just underline is there. Your name is another attribute, LOT is attribute, DID, department ID, and since. So these are the attributes. 5 attributes are there. Here already we know the department ID always depending on the SSN. Because SSN, you know, it is a primary key, already I said just now. So that all attributes are depending on SSN. Yes or no? Individually. Yes or no?
Yes, sir.
Yeah. So since it is a SSN is a key, so that and even sure SSN is again DID also depending on the SSN. So because everything must be depending on that. Now LOT is nothing but a the location of that particular department. So the department where it is working, so that is also depending on the department. The CSC department is working on the second floor, maybe the location, or IEC department working on third location, like that. So based on the logic, we can have the functional dependency. Yes or no? Clear this?
Yes, sir.
Clear this. Now you know very simple. Sure, SSN determines to DID, DID determines to LOD. So therefore, based on this, you know very well the mathematical simple relation. Your location is depending on DID, DID is depending on SSN. So directly we can write LOD is depending on SSN, so that we can write SSN determines to LOD. Correct? Yes or no?
Yes, sir.
Right. Means, you know, I am the CSC faculty. My faculty ID is 2004. Now, when if I am my faculty, based on my faculty ID, I know the department ID. Here, which department it is? Okay, he is the CSC faculty. Now, if you know the CSC faculty ID, then automatically you will tell where is the CSC department. Automatically you will tell go to the second floor. Even though these two things, if you know automatically, if I tell faculty ID or your student hall ticket number, if you tell 508, automatically I know last 3 digits. If I know 508, then I can tell, oh, you are the CSC student. Then go and sit to second floor, like that I will tell. Yes or no? Without asking department, I can tell based on your hall ticket number. Because then your hall ticket number is related to the department, department is related to the location. Automatically I will tell the location. Yes or no?
Yes, sir.
Yeah. Sure. Now, like that, we need to work on functional dependencies based on existing functional dependencies in the relation. Here, for that, we have two important things. Here, we are going to call closure set of functional dependencies F and F plus. Here, generally, whatever the direct functional dependencies we are going to find, those are called as F. Here means directly, means when you are going to extracted this SSN determines to DID and DID determines to LOD. But you are extracted based on these two, you are extracted one new functional dependency. If this functional dependency is not there in the relation, if these two functional relations are there, but you are extracted this new relation from these two relations, that is called as closure set of functional dependency, which is denoted with F plus. Are you clear?
Yes, sir.
Right. Now we are going to learn how to find the F. How to find the F? F is nothing but a directly functional dependency. Means if you are going to observe relation based on columns which is depending on other column, you can identify the F, that is a functional dependency. Yes or no? Yes or no?
Yes, sir.
Now, based on this function dependency, we are going to combine some of the functional dependency based on the some of the rules, that is Armstrong axioms. So now we are going to learn Armstrong axioms, means some mathematical rules. We are going to extract some new functional dependencies, that is called as F plus, that is a closure set of functional dependency. Here, closure set of functional dependency representation is F plus. Okay, now we are going to evaluate those closure set of functional dependency. Yeah, for that we need to we are going to evaluate functional dependency as well as closure set of functional dependency with the help of some mathematical formulas. Based on that, we can decide a normal form and we can apply. So that now we are going to learn. Basically, we have three Armstrong axioms. Rules are there. Armstrong axioms. This is a mathematical formulas. You know very well. You people are aware more because these mathematical formulas already you work in your mathematics. The first one is the reflexivity. For example, before starting this formula, here you please note it down. Here one relation R, capital R, which contains X, comma, Y and Z as a attributes over on relation R. Here R relation contains X, Y, Z, and let us consider X, Y, Z are the attributes of relation R. Okay, clear? All of you clear?
Yes, sir.
Yeah. Now the first Armstrong axiom, the first rule is reflexivity. What is the meaning of reflexivity? If X reverse subset are equal to Y, then please remember this reverse subset. If X reverse subset are equal to Y, what is the meaning of this X reverse subset are equal to Y? What's the meaning? For example, X subset are equal to Y meaning is what? X is a subset of Y. Here Y is a set. Now X is one of the part of Y, correct? Yes or no?
Yes, sir.
Some other people will write like this also. If Y subset are equal to X, then what should we write? Y determines to X. Clear? Some books are going to refer like this, but basically, okay, our book is going to refer, our Raghuram Krishnan and the base fourth book also going to refer. F reverse subset are equal to Y. Means reverse subset is nothing but here Y is a subset of X. Then we can write X determines to Y. Means Y is depending on X. Because X is a superset, Y is a subset. X is a superset, Y is a subset. Understand? So that we can write X determines to Y. So this is the original formula. Some books are referring this formula also. But you use this formula for reflexivity. Are you clear? Are you clear?
Yes, sir. Yes.
Right. The second formula is augmentation. Then what is the meaning of augmentation? Very simple. If you are identified in your relation, X determines to Y. Means Y is depending on X, you are identified. Then even you are identified, XZ determines to YZ. Means we are just multiplied Z both the sides. For X determines to Y, you are just multiplied Z both the sides. Is it equal or not? If I apply Z here and Z here, is there any problem? Hello?
No, sir.
No problem. Equal, right? Both we are multiplied with Z means it is equal. So that X determines to Y, then even you can write X multiplied Z with both the sides, XZ determines to YZ for any Z. So this is called augmentation. Are you clear? Are you clear?
Yes, sir.
Right. So the third Armstrong axiom formula. Please, these formulas are very important. Please remember, even note it down. In examination, they will ask, and these formulas we can use for normalization. Please. Transitivity means if you are identified X determines to Y and Y determines to Z, then we can write X determines to Z. Just now we discussed about here. SSN determines to DID, DID determines to LOD. So that SSN determines to LOD. That is what transitivity is, a common rule, you know, in your mathematics. If X determines to Y and Y determines to Z, that is called as, we can write directly X determines to Z. All of you clear? All of you clear?
Yes, sir.
Now these three rules are F. Here, these three Armstrong rules are called F. Just now I told you, functional dependency of F. You can call as a F. And these rules are sound. Here, these rules are sound. Here. sounding rules. That is the reflexivity, augmentation, transitivity. These are the three rules, basic rules, and these rules are Armstrong axiom are sound. These three rules are sound on functional dependency. Now, based on these three rules, again we can implement three rules. That is called as closer set of functional dependency. That is the F plus. Are you clear? These first three rules, reflexivity, augmentation, transitivity, is the sound rules of Armstrong axioms. If the reference is F, the representation is F. Here, based on these three rules, we are going to derive another three rules. These rules are closer set of functional dependencies. Here, the representation of this closer set of functional dependencies is F plus. Are you clear now?
Yes, sir.
Which you are telling. Yeah, now the first one is in this F plus is union. Here union means you know very well. Here union, you know, same meaning here also. If X determines to Y and X determines to Z. If you are identified this type of functional dependencies in your relation, X determines to Y, X determines to Z. Then you can apply union operator for this X determines to YZ. Just we are combining all. X is combining, X will come, YZ is combining, YZ will come. This is called union operation. Union operation. Are you clear?
Yes, sir.
Very simple. Even you can remembering also very easy. Now next one is the decomposition. The decomposition is exactly reverse of union. Decomposition is exactly reverse of union. So now if you are identified X determines to YZ, then we can write X determines to Y as well as X determines to Z with the help of decomposition. Are you clear now?
Yes, sir.
All of you clear about decomposition? Decomposition is known exactly reverse of the union operation. Clear? All of you clear? Hello?
Yes, sir.
Then the last one, pseudo transitivity. Very important. Pseudo transitivity means if X, you are identified if X determines to Y and YZ determines to P in your relation, then you can write very simple, Y is there, right? So that your XZ determines to P. Simple. Transitivity rule, how it is, X determines to Y, Y determines to Z. Then you can write X determines to Z, first and last. Here what happens? Pseudo transitivity. Pseudo, your transitivity is there, pseudo transitivity. Some part only is there. That is what? X determines to Y, YZ determines to P, so that you can write XZ determines to P. So this part is not there, right? That's why you are going to take up into left side. Then XZ determines to P. Clear? This is called pseudo transitivity. All of you clear this? All of you clear this? Hello?
Yes, sir.
Right. Yeah, now these six rules, these six formulas are called as Armstrong axioms. First three are the sound properties. Second three are the closer set of functional dependencies. Clear? All of you clear? If you're clear, I will go with one example and I will stop the class. That example is very important. All of you clear these formulas? Hello? All of you clear these formulas? Hello?
Yes, sir.
Yeah, if you are clear, then I will go with this example. Now I am going to take some contracts example. Contract contains, relation contains contract ID, supplier ID, project ID, department ID, project ID, quantity, value. Then how we are going to define the functional dependencies for this particular, based on this particular functional dependencies Armstrong axioms. We will learn now. Here just I will show you the example. Please, all of you, please try to understand. Any doubt or any clarification is there, please ask me so that I will clarify them. Okay? Is it okay?
Yes, sir.
Yeah. Now coming to the example. Now example is contracts of relation I am taking. First attribute is CID. Study CID. First attribute is a primary key. Just I am making this as a primary key. You know what is the meaning of primary key? Here, when you are using primary key, just now I told you the remaining all attributes you can depending on the primary key. Just now I told you that. Yes or no?
Yes, sir.
Well, now SID is the employee ID, contract ID, SID, and a JID. JID is a job ID and department ID. Next one is the part ID. Means every project is having some of the parts. Part one, part two means domains, or I can tell you part of the work. Okay, PID. Then quantity. So how much quantity and value. So these are the attributes I have taken for the relation. Here, instead of taking these CID, SID, JID, all these, here I'm going to take some symbols. For CID, I am taking as a C for representation of the attributes for easy. The SID for IS, JID for J, DID for D, you know, D and P, Q, and V. So these are the values just I am taking here, Q and V. Here for remembering easily, I am using this. Now coming to as per the things, you know, C is a primary key. Yes or no? Yes or no?
Yes, sir.
Then if the C is the primary key, how can we write? C determines to the first functional dependency. Directly we can write C is a primary key, so that we can write C determines to C S J D P Q and V. So this is the basic, means I'm writing here F. Okay, functional dependency. Okay, F plus we will do it later. First of all, we have to finish up with F. Yes or no? This you know. Yes or no? Yes or no?
Yes, sir.
Now I am going to do the second one. Here, you know the second one. Here, project purchases each part using single contract. Exactly. Here, every project is going to purchase. I am going right here. Project purchases each part. Part means some of the part. For example, login page is one part, database is another part, like that. Okay, part using single contract. Exactly. Here, first of all, I have to finish up this part, then the payment will come. Next, you have to finish this part, then other payment will come. Here, like that, here always the contract is depending on the job of the part, compulsory. So whatever the job they are doing and how much part they have to perform. So that here always the contract is depending on what? Job and part of the project determines to the contract. Yes or no? How much job they performed and how much part they are performed, so that they can release the contract. So that is the contract. Contract always depending on job, how much job and how much part of the project. Clear? Basically, based on the relation, we can understand F. Clear this? Hello?
Yes, sir.
Yeah. Now coming to third function. Here, department purchases at most one part from the supplier. Exactly. Here, every department is going to department purchases at most one part from a supplier. Here, department purchases at most one part from a supplier. Here, supplier who is supplying. Project means any construction project or anything you can take it. Who is supplier? Supplier is supplying, but a department purchases at most one part. Here, out of all the parts, only at least at most one part from a supplier. Here means here always the part is depending on the supplier and department compulsory. Here the purchase is the purchase ID PID, the part ID. Here always depending on the supplier and department, because every department is going to take different. For example, the engineering department will take some other thing. For example, construction, if you take the masonry, something people will take something. The maintenance people will purchase something. The electricity department will take something like that. Here always here the part ID depending on supplier and department. Supplier, department determines to part. Means they are compulsory. What part? That part ID means that whatever the part is going to complete, that must be supplier. Supplier is going to supply, and which department is doing that. So that must be done only based on the supplier and department. These three functional dependencies are come from the relation. When whatever the relation we are identified, this contract. Now we are going to do the closer set of functional, that is the F plus. We need to find the closer set of functional dependencies of this F. Here, that's why first of whenever we are going to do a functional, whenever we are going to find the functional dependencies, first of all you need to find the functional dependencies. That is a sound functional dependencies F from the relation. After that, we are going to extract closer set of functional dependencies of existed these functional dependencies. Are you clear? Are you clear? All of you clear?
Yes, sir.
Right. Now, how to find the closer set of functions? Just now we discussed about the formulas. Okay, Armstrong axioms, 6 Armstrong axioms. Here, based on that, we need to do that. Here, when you are going to observe based on this, here, from I can otherwise I can use text. Okay. From JP determines C. So that is what third, the second one. JP determines to C, and here JP determines to C and C determines to. What is that? C determines to C, S, A, D, P, Q, V. Now, from these two, you can apply transitivity rule. Are you clear? What is the transitivity rule? Can you tell any one of you? What is the transitivity rule? Hello? What is the transitivity rule? I'm not getting your voice. What is the transitivity
X
rule?
determines Y and Y determines Z, then X determines Z.
Then here Here JP is the X and Y is the C. Now Y is the C is determines to Z. Then you can write X determines to Z. Then what we will get? Another functional dependency, closed set of functional dependency. What is that? Tell me. JP.
JP determines CS JDPQ.
CS JDP QV. Are you clear this? Are you clear this?
Yes.
Right. Very good. Now this is one functional dependency you are extracted, closer set of functional dependency for existing functional dependencies. The next one is here. From SD determines to P. So from SD determines to P, you apply augmentation rule. So what is the meaning of augmentation rule? You can add any one of the variable both the side, so that is possible. Yes or no? Yes or no? Hello?
Yes, sir.
Right. Why I am adding, then you can understand. SD determines to P is there, even though you can write like this also. This is the equation 1. Now this is equation 2. Now this is equation 3. Now we got equation 4. Now we are planning for equation 5. For that, just if you are observe, SD determines to P, SD determines to P. Now already here SD determines to P we have taken. From this we have to do it augmentation. Means we have to multiply some other variable both the sides. Okay. Okay. So now I am going to apply augmentation rule on this SD determines to be. I am going to apply J both the sides. S, B, J determines to Pj. Is there any problem based on the augmentation rule? Is there any problem?
No, sir.
No problem. Now this is what? Equation number 5. Means we are doing these many functional dependencies. Now, based on this, from SDJ determines PJ and JP determines. Where is the JP? Which one? Which one? Okay, this one. Fourth equation. JP determines. What is that? C, S, J, D, P, Q. So from this, here I am applying pseudo transitivity rule. Sorry. SDJ determines PJ, JP determines, no, it is only transitivity, right? Not pseudo. Yes or no? Hello?
Yes, sir.
Transitivity. So based on this transitivity rule, what we will get? What will get? SDJ, tell me, determines CS, J, D, P, Q, D. So this is equation, means functional dependency of 6. Are you clear? Are you clear?
Yes, sir.
So finally, from equation 1, finally the equation 1, that is from C determines to C, S, J, D, P, Q, V. Now you can apply decomposition rule. Tell me, what is the decomposition? Hello? What is the decomposition? Are you there? Is this my voice audible?
Yes, sir.
Yeah, what is the decomposition? Just now we discussed, right? Decomposition. Decomposition. If x determines to yz, then we can write x determines to y, x determines to z. So that from formula 1, what is the one? C determines to CS, JD, PQ, as per the primary key rule. Then we can write. For that, you have to decompose it. What we will get? What we will get? Tell me. Hello? Are you following?
Yes, sir.
Tell me now. If you are following, why you are sleeping?
No, sir. So C
Tell me.
determines D.
D. So it is going to decompose.
Exactly.
So these many formulas will come. 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12, 14. 14 formulas will come. Correct? So, have you understood?
Yes, sir.
So all these are called F plus, closer set of functional dependencies. So based on this Armstrong axioms, we can define the closer set of functional dependencies. Like this, we need to define and identify the functional dependencies. After identification of the functional dependencies, you need to check which is suitable for which normal form. Based on that, we are going to apply normal forms. Now, all of you clear about this functional dependencies? All of you clear about these functional dependencies?
Yes, sir.
Yeah, very good. Sure. If it is clear, in the next class onwards, we will discuss about the normal forms.